A very good evening to all of you. Before I started, let me thank Siva and the team at ICTS for giving me this opportunity. Actually, I'm quite excited to give you this talk today. I started Semantic Web India out of sheer passion to build semantic web applications which could find some real life application use cases in the Indian context. And I would actually be sharing my journey. 40 minutes is actually very less time for me to cover this broad topic, but what I really hope to do is probably kind of expose you to what this technology is all about. What is its how is it placed in the data science canvas, and maybe some of you might be interested to pursue this in your future academic journey. So a little bit about myself. I did bachelor's in mathematics from Delhi University, and then went on to do master's in statistics from Indian Statistical Institute, Calcutta. So Siva and I are batchmates, and post that I went on to join the industry, worked there for 20 years, various roles, and probably that's when the urge to do a doctoral degree really was resounding within myself, when I took a break from my corporate career sometime in 2013 and completed PhD in data science from IIT-Bangalore. And the area of interest, the research work that I did was largely in semantic web knowledge representation, graph networks, and how they all come together to understand data and its context better. So for about a year, I was working with a not-for-profit organization, but then I realized that I need to do something to basically get this technology to work on some real life application in India, and that's how I dedicated this startup to precisely this technology. So let's start. So today, what I am going to do is give you the idea of semantic web in a nutshell. We'll talk a little bit about why this is so important. How different is it from your standard AI and ML algorithms? What goes into making a semantic web application? I'll be taking you through some examples of some real life applications from the industry. I represent the industry, so that's something that I would do. I'll also be discussing some research work that is happening at the moment. What are the cutting edge research areas in semantic web? And maybe I'll end the talk with what we are doing at Semantic Web India. So let's begin. Semantic web in general, if we, just like you browse through your World Wide Web, right? You access a particular website. Through those links, you tend to access other pages which are of interest to you. Imagine if you could do the same thing with data. If a piece of data could miraculously lead you to other pieces of information and knowledge in the same way as you traverse web pages, right? Now that's the idea about creating this web of knowledge. So how do we do that? Every statement regarding the world, it can be encapsulated into three parts. We call it the subject, predicate, and object. So semantic web is all about making statements or facts about what you see around you, about all objects and concepts in the world in a tuple form, a subject, predicate, object form. And to explain this, I have taken this example where I've actually picked it up from DBpedia. You all must be aware of Wikipedia pages, right? So So parts of the structured information from Wikipedia was converted into a semantic web or a knowledge graph based on semantic web principles, and that is called DBpedia. And there, for example, if you were to go to the wiki page about India, right, and all of that structured information is encapsulated in this vocabulary, and hence, if you look at this very simple thing that just two tuples here, as you can see. One of them defines, it says that India's capital is New Delhi. The other one says that India's currency is Indian rupee. So as you can see, each fact has got a head, which is called the subject, and then there is a predicate, and then there is an object. Now, what makes semantic web unique is that each of these objects that you see is a URI, a unique resource identifier, and it uniquely defines this resource in the vocabulary that it has been defined. So here I have picked up DBpedia, but there could have been some other vocabulary that is defining India in some other context, and that could have its own way of representing the same resource. So semantic web in a nutshell is about representing knowledge. It's a knowledge representation formalism. So when you talk about formalism, then obviously there has to be some amount of publishing standards, just like an HTML page, right? Today anybody can create a page, an HTML page, and if you follow the standards of notating your HTML page, then you can actually access it from any OS, any computer, right? Because that formalism is interoperable and it is consistent. In a similar fashion, to represent facts in semantic web, we have to follow some publishing standards. And the most important advantage of representing data in this form is that it facilitates information retrieval and data integration, and we will see very shortly how does this happen. Why is it so important? So I have taken an example from a biomedical domain, because this is the domain that largely puts semantic web to use. So here, let's take an example of an organization which conducts a lot of lab experiments data. Typically, lab experiments data would contain, the sample, on which the test is being done, and the data set that is associated with the sample, which is the digitized form of that particular sample. And then you are actually making some observations, and there are measures, and they're being reported by a particular person who's working in a specific department. Now, typically in a lab, there are tons and tons of experiments that are being done. And if we really wanted to, typically get some unified knowledge from all these experiments, because typically lab experiments tend to be connected. You never know, there could be some, explicit or implicit relationship between one experiment to the other, and these become very important, especially in a biomedical domain, because the chemicals that are involved in a particular lab experiment, or the samples that are being used, they all are interconnected in some way. They could be interconnected, and it would be very useful if I could literally connect these pieces of data together. So here what we have done is, we have used the vocabularies which define biomedical concepts, like examples like gene ontology, which defines the gene symbols and the proteins that genes are involved in. And similarly, open biomedical ontologies that help you define biomedical terms, and so on and so forth. So now, if these lab experiments data could be annotated, could be grounded using these vocabularies, and suddenly what you achieve is what is called a kind of a knowledge graph that links all these individual pieces of data. And now this knowledge graph is rich because I can infer new facts, and I will tell you how in a few minutes. I can do a multifaceted search. I can actually write very powerful natural language processing routines, which can actually go and retrieve data from this knowledge graph. But largely what it does is that it generates a network of linked data that can now be traversed through these links that get connected, that get created. And one of the most important things that happen is in semantic web that happens is that you tend to decouple data from the metadata itself. So what does that mean? So there are, if there is a particular department or an organization that is uh, having a huge amount of domain knowledge in a specific topic, then they take up the responsibility of creating a domain vocabulary around the same. And as long as my data can link to that particular vocabulary, then I'm able to harness everything about that particular data. So semantic web is all about connecting those data silos through common vocabularies that are created by domain experts. So there are some building blocks of semantic web, and let me just probably quickly check with a show of hands in this particular, just very quickly. I just want to get a show of hands from the audience. I had sent some reading material. How many of you were able to read it? Because the future examples heavily depend upon how many of you could really go through those links, even if you didn't go through the whole thing, at least to get an idea of what we are talking today. Maybe you can use the raise hand or something to just let me know whether were you able to go through those links.
So Asha, I think they were just posted on the website as a title and abstract, so people may not have seen it. I think it might feel.
Okay, no problem. So just another quick question. Have you been exposed to relational databases like SQL, MySQL, or some form of tabular data representations? How many of you would be okay? Yeah, I can see. Yeah, fine. Because I just wanted to understand what other formalisms are you comfortable with? Do you know the relational database form of? Yeah, fine. Okay. Yeah. Okay. Right. So the building blocks of semantic web, let's understand that. So these terms are very common. What is an ontology? What is a vocabulary, a namespace, or a knowledge base? Let me explain that first. So as I mentioned, a semantic web representation is to represent the facts in subject, predicate, object tuple. So like as you can see, I have augmented the same thing in using a few more tuples. Now this collection of all these facts is what is called a vocabulary or an ontology or a knowledge base. You use these terms quite interchangeably. The namespace here is actually this. Can you see this? http dbpedia.org. So this particular set of tuples belong to the namespace of dbpedia.org. Similarly, if you can see, what have I done here? I have said that India as an entity is a type of country. And which namespace is defining this object called country? It's the schema.org vocabulary, so, or schema.org namespace. So this particular portion of that URI is called the namespace. Now, before I can define anything on the semantic web, I need to actually formally create a few classes or properties and stuff like that. So, for example, country is a class in schema.org. Country is also a class in the dbpedia.org ontology. And a country class typically might have the following properties. For example, the name of the country or the label of the country, the currency that particular country has. So basically the properties of a particular class that define that class completely. So defining this basic schema is what is called as the T box or the terminology box. Once you define it, then you start to define the instances of that particular vocabulary. So India is a specific instance which is of type this schema.org country. So these light colored orange boxes that you see here is the T box of that particular vocabulary, whereas the actual instances form what is called the assertion box or the A box. Now, the formalisms that we typically use to define a class or define the property are RDF, which is the Resource Description Framework, RDF schema. OWL is called the Web Ontology Language. So here again, I have given those examples. So the RDF schema actually has the property called RDF type. So if you want to define a class is of a certain type, then you use the RDF type property. Similarly, RDFS label comes from the RDF schema vocabulary, which actually you can define things like labels and many more properties. There's only a subset of what I have shown here. If you want to kind of say that something in one vocabulary is equivalent to some other class in some other vocabulary, like here we are saying that schema.org country is equivalent to dbpedia.org country. So what it really means is that if I'm using the schema vocabulary to define a country, it is actually the same as what dbpedia refers to as country. And once you define all this data, just as you have a SQL statement, for example, you define tables and columns and all that in your SQL database, and then you have the SQL syntax to retrieve all that data. Similarly, in the semantic web parlance, you have what is called Sparkle to retrieve the data. Now, there are some pre-existing vocabularies, if I may say so, and these are part of linked open data cloud. And so we don't go ahead and reinvent the wheel, right? So suppose I'm creating a specific vocabulary which is dealing with persons and objects, then there are already many vocabularies that have defined people or persons. For example, FOF is a vocabulary that defines friend of a friend. Your LinkedIn, the professional network, the LinkedIn uses a lot of this FOF vocabulary. Similarly, schema.org. So just the engine behind your Google search, right? When you type in a restaurant, or vis-a-vis you type in, say for example, a refrigerator, it somewhere understands that you're looking for information on restaurant, and it tries to give you related information about restaurants. For example, restaurants have 5-star ratings, and there are many properties. Restaurants is a particular, it's located in a particular place. So when you're searching for something, it will say so many restaurants are within 5 kilometers of your radius. Similarly, on the other hand, if you were searching for a washing machine, the entire thing seems to change, right? And how does Google really understand what you're searching for? So in behind the scenes, it is using the schema.org to actually annotate each and every page, and that gives that enables the semantic web on that particular data content, right? So that this is how it works. Similarly, there are ontologies for organizations and so on and so forth. There are other vocabularies, especially in the medical domain, such as the Unified Medical Language System, which is largely used for storing electronic health records. You have good relations ontologies to store goods which are going to be transacted on a portal, for example. So with that, let's see how this works. Now, just one second, I'll just move this somewhere here. Now here I have shown you the difference between how the same data which you see built on an RDBMS, how that varies from what you see on a knowledge graph. So let's try and understand what's happening here. Say for example, I have a very simple system in my relational database world, where I have states which are identified by an ID, and then the name of the state, the population, and then the capital, and whoever is the chief minister. And then I also have a separate table that holds the state and its respective district. I have a third table which is storing the indicators of that particular state. Here I have used literacy, but we could have literacy, healthcare, and so many other indicators. If I were to denote the same thing in the knowledge graph parlance, then what I'm actually doing is, first, this particular portion, I am actually building the terminology box. So I'm saying that there is a state class. The state class is linked to the city class through the property called has capital, and similarly state is linked to the person class from schema.org through the has cm property. And in all these cases I'm not redefining these classes, right? So person I'm reusing from the schema.org and so on and so forth. Similarly, the indicator class I'm reusing from a very well-known vocabulary called the simple knowledge organization system. So in a T box, there are multiple formalisms. A property can connect uh, um, two object nodes where each one is representing a class, or a property node can actually be connecting an object to a literal value. For example, here as you can see, the abbreviation is a literal value. It's not defining a class here. So that's where you have the difference between the object property and the data property. So once you define the T box, then the next step that you do is you define your assertion box. And now basically you're populating the data, right? You're populating all of this rows that you're seeing. And here is how you do that. You say that Karnataka is of type state, Bengaluru is of type city, and the fact that Karnataka is linked to Bengaluru through this has capital, and so on, right? So this is how you build the T box and the A box in semantic web. Now, what is the advantage that I find here? So if I were to work in an RDBMS application, for the machine, Karnataka is no different than a 9-character string, any other 9-character string. It really does not understand what really this means, right? It's the way the people use these systems. For example, the person who's using this application knows that the states and the state district is connected via this ID, and the fact that this is a district within Karnataka, right? Now, imagine that there are multiple, departments in the government. There is Department of Health and Family Welfare, which is actually storing its data related to the health indicators. There is an education department, which is storing data related to the education related indicators. Now, there is no way that these two systems are going to talk to each other unless they follow the same naming convention, right? It becomes a nightmare to make two departments, although they are talking about the same entities, to talk to each other. And here is where you end up creating what is called a data warehouse or a data lake, where you try to map what one department calls as state or one department calls as an indicator to the same columns which are used in another department's database system. So that particular problem is largely resolved in semantic web, because each and every entity that you are referring to here, it's no longer just a string of characters. You are referring to Karnataka as that URL which is uniquely defining Karnataka in a specific namespace or in a specific vocabulary. So now if the departments were actually using semantic web to denote whatever they're talking about, there would be hardly any problem in integrating data from multiple departments, because both the departments end up referring to the same entities, right? And that's where the reduction of data silos, the interoperability of the applications, and most importantly, I'm able to harness the data semantics. Why is that so? Because now when the machine looks at Karnataka as that URL Karnataka, it understands that Karnataka is actually a state in the southern part of India, and that there are it neighbors, say for example Tamil Nadu, and so on and so forth. So now it suddenly starts to get a context for that particular data, which is largely missing in a pure RDBMS application. So what is the role of semantic web in a data science canvas? So typically, if you look at raw data, you use a set of routines. Now you can see that I have included the whole gamut of processing. You can actually do very simple analytics, or you can use the higher end AI or ML routines. But ultimately, what you are trying to do is you're trying to understand the patterns in your data, and you are trying to predict some outcomes. And these outcomes actually mean something in the domain of your interest, right? But typically, it's not so simple as this. So once you're applying your machine learning or any form of routines on your data, and the outcomes are predicted, there is a set of domain experts who work on those outcomes. They probably use the outcomes to refine the algorithm, to augment the input, until they get outcomes with considerable accuracy. So semantic web comes right in the intersection of, as you can see, it comes in the intersection of your the algorithms that you're trying to write, and also it tries to replace or at least semi-automate the inputs that a domain expert is trying to provide in this entire scenario. So by and large, it will help you to intelligently augment your algorithms with the right set of features that are dependent on that particular domain. It can do it because now it understands the data along with its context. And this whole genre of building your AI and ML augmented with semantic web is leading to what is called context aware or context intelligent applications. So let's see if you're able to access this particular quick quiz. All you have to do is type in slido.com and then this particular ID, or you can just use this to scan. Will you be able to, are you guys able to do this? Just type slido.com on your mobile phones, or if you have a desktop in front of you, desktop or laptop, and then use this ID to. Shiva, will the audience be able to do this?
Sorry, I was on mute. Yeah, I think yeah, some of them can do it. They should have either a phone or a laptop.
Yeah, sure.
I'm logged on from the thing.
Yes. Yeah.
It asks for cookies and all. Okay, I'll allow.
Oh, is it? Okay.
It's okay, I'll allow.
Okay. Yeah, sure. So I can understand, because it's a fairly, although it has been around for a decade or so, the applications in India are just about catching up. Right. Okay. So this gives me a good picture. So let's move on. Now, typically, what goes on into building a semantic web application, as you could see, we first have to define the ontology. Or if you're using something which is well established, you pick that up, which pertaining to your domain. The second important step is to generate those instances, and this is quite hard, So you either people do it manually here, and or there are you use a lot of AI or machine learning to actually build the data semantics from your structured and unstructured data. And what really happens here is, when you look at any form of data, whether it is in a tabular form or unstructured for that matter, each of those data point has to be disambiguated, right? That's what I meant by the entity disambiguation. So when you look at something like a Karnataka or a Mysuru or a Bengaluru, you need to assign it assign to it the correct disambiguated entity from the right vocabulary, right? And that's how you generate the instances. And hence, if there is a mixture of either through the user interface or ontology matching, you generate the instances. And then once you have created those tuples form what is called a knowledge graph, right? It's a knowledge graph because every subject, predicate, object is a piece of knowledge, and each of these are connected to each other, and hence, it's a knowledge graph. And there are multiple ways of managing the knowledge graph. As I mentioned, just like you have SQL, you have Sparkle to do the inserts, selects, and so on, or even bulk loads. One very important task in managing the knowledge graph is to verify it, because you have used the automated process to generate the instances. So if you have not linked the data properly, then obviously all the downstream processes that you do would be erroneous. So there is a verification process that we have generated the right knowledge graph. And finally, I use the semantic intelligence. I can now reason just like a human brain does, and I'll just tell you, in a few minutes how we do that. And you can apply all kind of algorithms and rules and generate new facts, and really harness all the semantics that you have generated from your raw data. Now, once you do this, how does all of it come together? You will obviously have a visualization component, some front-end layer. There will be an application layer that helps you to convert the data or retrieve the data from the knowledge graph. And you have to store the tuples somewhere, right? And that storage typically is done in any knowledge base which can store graph database, and typically Virtuoso, open source, onto text. These are all typical graph databases. These are some of the companies which are working actively. Have picked up some of the top ones. In India, we still do not have a company which is totally dedicated, and that's where we are trying to make a mark. Build something which kind of builds applications particularly for the Indian context. Semantic web applications have a lot of usage, specifically in the life sciences domain. As I explained through that example, gene ontology has been around for close to 20 years, and it's a very, very active vocabulary, and people use it to detect novel relationships between phenotypes and genotypes. Bio to RDF is again a very important endeavor, which actually links many of the biomedical vocabularies under one umbrella. And in fact, we are using this extensively for some of our work that we are doing in the genomics domain. And likewise, I've mentioned about UMLS and OBO. In fact, there's a journal dedicated for for research that is happening in the semantic web and the biomedical domain intersection. There are a lot of active areas of research in semantic web. Typically, ontology alignment itself. For example, if there are two ontologies which are talking about a similar concept, how aligned are they? What is the overlap between them? That's a quite active area of research. This is the most hard part, generating the semantic knowledge graph from raw data. In fact, my own thesis was in this particular domain. This is really, again, another active area of research, because we still are far away from understanding unstructured data, right? For example, can we pick up a random PDF document or a random blog and convert it into a knowledge graph which is grounded with some vocabulary? And there are quite a few of these. Once you create the knowledge graph, and you can create some very interesting question answering systems. You can do efficient querying by your natural language generations and all that. So there are a lot of these research areas in the semantic web. It has got strong relationship with math, especially graph theory, and I'll take a few minutes to explain that. So this Sparkle that I was mentioning is ultimately what it is doing is it is actually doing set operations at the backend, right? So you have a whole database of tuples, and each time you issue a Sparkle query, you're actually selecting through either an intersection or a union, or you're doing um, a minus of one graph from the other graph. So it's, so behind the scenes there's a lot of set operations that are happening. The other important area where, in specifically our organization is working on to build some interesting insights from the graph is the intersection of linear algebra and your graph. So typically, look at this particular matrix, right? Now this matrix has been generated from a knowledge graph, where, as you now understand, that within a knowledge graph there are nodes, and there are connections between these nodes, right? So A, B, and C and D, if they denote nodes, so a -1 is the source node and 1 is the end node. So here it basically, each row determines a link. So the first row says that there is a link between A and B. The second row says that there's a link between B and C, and so on and so forth. So this is called as the incidence matrix. And now when you apply certain matrix operations on this, it tends to give you some very interesting observations as to which nodes are coming as part of a cyclic routine, for example, and which of these nodes are redundant. Simple matrix operations can give you those results. The same thing can be represented as an adjacency matrix as well. An adjacency matrix just says, it's a here each column was a node and every row was a connection, right? Here every cell is actually, every row and every column is representing it's a square matrix, and a 1 actually indicates that there is a link between the two nodes, right? So that's how the adjacency matrix is created. And certain operations on the adjacency matrix actually give you some very important solutions to what is the shortest path between, say, two nodes, which of the nodes are influential. The famous PageRank algorithm is also derived from the adjacency matrix. Lastly, there is a lot of logic that one can apply on knowledge graphs. Simple logic items such as the transitive logic. If A implies B and B implies C, then A implies C. So here what it really boils down is that if a particular node is related to another node B using a particular property, and that property is transitive, and if the same property applies between the nodes B and C, then I can probably say that A and C are related with that particular property. The famous example here is in LinkedIn or in Facebook. It tries to tell you that you might be friends with these people as well, right? Okay, I just have about a minute, I guess. So these are so how do we do that in semantic web? We do that using the web ontology language, where we are able to reason new facts. I am able to do graph inferences. I am able to figure out the truth of certain statements, and so on. So the semantic web core concepts are very closely linked with just basic, your set theory, matrices, and logic formalisms. So I'm going to skip this because we are really short on time. Shiva, how much time do I have? Do I really have to finish in the next 2-3 minutes?
We take over 5 minutes maybe?
Yeah, 5 minutes should be okay. So now let me just show you some examples of what we have made. Maybe I'll just take you through one example. So a lot about the metadata regarding India, right? So, things like the various districts, the villages, the local bodies, all of this information is scattered in various public domain portals. And when we were building some application which was using the publicly available data, we realized that this information is so scattered. We are not able to find a wholesome view of a particular entity, for example. And that's what motivated us to create Bharti. I'm just going to give you a quick are you all able to see my screen?
Yeah, we can see. Yeah.
Yeah, you can. So here, as you can, this is so behind the scenes there is a huge knowledge graph which has brought together a whole lot of information from multiple publicly available information about India's metadata, right? So for example, if I say what is it that you know about an entity called Hosur, so it actually tells you that I know about Hosur as a sub-district in the Tamil Nadu uh, Krishnagiri district. There are also a whole lot of villages called Hosur in Karnataka. So now when we have built this entire knowledge graph, right, and now if I go ahead and load any of these data sets that are publicly available, which say for example talk about some indicators or some data at the sub-district level or at the block level, and I link and I actually annotate that data using Bharti's entities, what really happens is all of those data sets now tend to get connected, and I can do all my complex operations regarding rolling up of data at any level, from a village to a sub district or a village to a district and so on and so forth, right? Let me show that example as well. So we use this in multiple places. So let me just show you how we built something called a semantic analysis of COVID data. So all of this data we just picked up from public domain, and we realized that while there are many portals that talk about data. For example, you can either look at the data at the district level or you can look at the data at the state level. But we said, can we apply some semantics and check out how these things work? And when we created all those links from the semantic web links to the data, now you will see what happened. We actually say we pick up a district like Bengaluru urban, and then we say within the 100-kilometer range, say you show me the data. So this particular stuff as to what all is within the range of those 100-kilometer, we really didn't have to do much, because all we did was, once we semantically linked these entities and then we looked up another vocabulary called geo names, the entire graph almost got created automatically, right? And now if you said that show me what is happening in my neighborhood, or show me what is happening across events, say for example, there is also something called an event based analysis, right? So we use the event ontology to link. So actually I can look at data across space, across time, and across events. I think I will have to stop here. So let me just get back to the PPT. Yeah, I'll just probably end with the thought that data just on its own is actually meaningless. As you add context to it, obviously it turns into information. But when you really put in the semantic web components to it, that's when you can reason with it, you can apply rules, and then your experience with context aware applications starts to become a reality. And that's exactly what Semantic Web India is into doing, to building these kind of context aware applications for the Indian context.
Yeah, thank you very much.